Ok, tout ça, c'est les effets de la grève de la RATP. Okay, so it's 11, and sorry for the chaotic start of this seminar of today. And just want to introduce Roland Diehl, and welcome to Paris in person. And we are very glad that you made it. And I will leave Nikos to introduce Roland, and also then to take the questions and coordinate the discussion. So,
thanks. So it is a great pleasure for me to introduce Roland Diehl from Max-Planck-Institute of Extraterrestrische Physics. I know Roland for a few decades now. We basically started our career at about the same time. It was in the early 80s that the American satellite HEO-3 made a major discovery. He discovered an emission at 1.8 MeV, characteristic of the radioactive nucleus aluminum-26, which has a lifetime of about 1 million years. So this meant the implications of that were quite profound. It meant that, because it has such a short lifetime, it meant that aluminum, and by extension other nuclei also, continuously and even produced in the galaxy, obviously by stellar nucleosynthesis. And we know that it is produced by explosions of supernova. We know that there are about 1 or 2 supernovae every century in the galaxy, which means that it was a product of about 10,000 supernovae in the last million of years. Of course, at that time, the resolution of the instruments was low, and it was detected in the general direction of the galactic center. It took about 1 more decade with the American satellite Compton Gamma Ray Observatory and its instrument CONTEL, of which Roland was the PI, to make the cartography of that emission and see that it was diffused all over the galaxy in the plane of the disk and preferentially in the spiral arms of the Milky Way, which is understandable because core collapse supernova explode mostly within the spiral arms. And after that, Roland was the major working on that topic. And later, in the 2000, there was the next satellite, ESA's integral satellite, and Roland played also a major role in that instrument. He was PI of the spectrometer of integral, the SPI spectrometer. And they made a series of interesting discoveries, this time for the characteristic annihilation line of positrons in the Milky Way. But Roland played also an important role in structuring the field of cosmic rays, of cosmic radioactivity. So by organizing biannual workshops, which federated the community and ended up with a monograph on the subject, Astrophysics for Radioactivities, a highly successful one, which was published in Springer and re-edited about a few years ago. So I think he is the best placed person to tell us about this field of nuclear astrophysics, which is astrophysics with cosmic radioactivities. Thank you, Roland, for coming here, and the floor is yours.
Thank you very much. It's a great pleasure for me to be at the ERP again. I don't know if the sound works now for the internet. There seems to be some problem.
Yeah, it works, but it's not very good.
So I don't know if I have to unmute myself here, maybe.
No, don't do that.
Maybe
Did you deactivate the sound from the?
yeah, you did.
That's just deactivated.
Don't know how much. Can you try again?
Yeah, I can also use the other microphone if you like.
Yeah, that was one.
Is this better?
Perhaps so.
Okay.
Is that working better, or?
Yeah, it seems so for the moment.
And we found a problem then. Sorry for this.
Okay. Let me use this one, so now you can hear me. Let me repeat that it's a great pleasure for me to be here in person We have had 2 years of Zoom meetings now, and it's really great to be able to see a few faces here in the room. And we have also people in Zoom, so welcome everybody. I'm going to talk about nuclear astrophysics. This is about the fusion reactions that made the elements and nuclei in the universe. And my field is gamma ray astronomy. Nuclei are bound by the strong nuclear force, and that has typical energies, binding energies of MeV. And this is why I talk about radiation that is also MeV radiation. Talking about, oops, I have to get that going here. Yeah, sorry. Typical binding energies are MeV, and if you want to do fusion reactions in cosmic environments, then you have a thermal plasma, and the thermal plasma has to have energies so that the kinetic energy of the particles from thermal motion overcomes the Coulomb repulsion. And that, in effect, leads to typical reaction energies of about 10 keV from the overlap of the tunneling probability for getting into the nuclear potential and the thermal energies as shown here. This is the so-called Gamow peak. That's the nuclear physics that you have to apply in cosmic environments. And now in cosmic evolution, we know that these reactions occur typically inside stars, in the centers of stars, and also in stellar explosions. And so this is my illustration of the cycle of matter as it happens throughout the universe, forming stars, and then these stars evolve, and they have these nuclear fusion reactions in their cores. Finally, the most massive ones of them explode very fast. The smaller ones take a longer time. And this is the way how material is being returned into the galactic gas reservoir. And that's the way how the abundances as we have them today have been built up from primordial gas that mainly was hydrogen and helium. And if we want to look at that in a little more detail, then we have to basically solve the equations of cosmic chemical evolution, which trace how material from the galactic gas reservoir is turned into stars, then evolves, and is then returned back into the gas reservoir again, enriched by the products of nuclear fusion. And this is the first equation that basically states the budget of material between gas and stars. And you have to do a little more than that. You have to then look at how much material comes in the return of this gas from the fusion reactions. And that are the stellar yields. And there is more to this gas budget because there are inflows and outflows of the galaxy. And in all of that, chemical evolution is a complex problem that has been treated by many people. And my part is only to address some aspects of this. So I will be talking about how yields are evaluated, how can we find out how much material in terms of new fusion ashes we get from certain sites, and how the flow of matter is returning this newly produced gas back into star-forming material. So in a global display, I would say massive stars are the most important ones. So on the right-hand side, you see a few arrows that represent the different sources. And the first sources that started to do nuclear fusion were the most massive stars, and they are dominating because they evolved the fastest. And then there are secondary sources that are the narrower blue arrows on the right-hand side. Some of these started as early as the massive stars because they are rare types of core collapse supernova explosions. And some other sources started later because they are the result of binary interactions. These are the type 1a supernovae, where a white dwarf accretes material and eventually leads to an explosion of the white dwarf. And that starts quite a bit later than the massive stars. And the same is true for neutron star mergers that have been discussed recently. So with this global picture for cosmic nucleosynthesis, we basically have this understanding as displayed in the top left graph. This is the abundances of the cosmic elements as a function of the atomic mass number. And you see here that the distribution spans a large order of magnitude, 12 orders of magnitude in abundances, the most abundant still being hydrogen and helium. But then there are secondary peaks. For example, the green one in the iron group area is a local maximum. Then there are some maxima at the low abundance regime for the very heavy elements that come from so-called R and S process. And all of this is a convolution of nuclear physics with astrophysics. And this is why this is called nuclear astrophysics, because the stability of nuclei is one of the determining forces. And the second determining force is to create an environment for these nuclear interactions. So when this picture was published maybe 20 years ago or so, many people thought, oh, cosmic chemical evolution and nucleosynthesis is basically fundamentally understood. There are many small things that need to be solved, because if you see on the right-hand side the table of isotopes, then the yellow parts, they are basically where we don't know much about the properties of nuclei. And so that's why laboratories are being created that make these rare nuclei and trying to understand the nuclear binding in these nuclei. But also on the astrophysical side, there are quite a few things that are still issues in how chemical evolution works. So on the top right, you see a graph like typically Nikos has been making these graphs, where the abundance of elements as a function of metallicity is shown for different individual elements. And you see that the red lines that are shown, sometimes they go through the data points and sometimes they are systematically off. And so this is an illustration of some of the issues that we have in this chemical evolution that I was describing earlier. Then there is a second thing shown on the second graph from the top. If you look at the rate of core collapse supernovae, and you try to measure that, and you try to combine that with the chemical evolution that I showed, then there's a mismatch. And we do not know actually the rate of core collapse explosions, even in our galaxy, because the observations don't match with what you need for chemical evolution. Then there's a third aspect that involves chemical evolution in detail for the R and S process. For the R process, mainly the sources that come from binaries. The question is, when do they start adding important contributions in this cosmic evolution? And this depends on binary evolution. And so binary evolution is one of the hot topics these days in general in astrophysics, and it has these implications that we don't know how the delay times are. So this is the evolution shown for the europium abundances versus iron abundance or metallicity. And for two different delay times, you see you have two different models, and one model fits a little better, but one could say there is no perfect agreement yet. And another topic has been brought to us by Gaia. Gaia has made wonderful measurements of stellar positions and dynamics. And with this, we have learned that the galaxy is not a closed system. There are many stellar groups that have actually been inherited from probably other smaller galaxies that merged at some time with the galaxy. And that is another complication that has to be figured in and worked into the chemical evolution equations. So with all of this, I think observations are what will carry us further, as you see also from these Gaia observations. And so one can ask yourself, how can you observe nucleosynthesis events directly? That would be the nicest thing, to have a source of nucleosynthesis that makes nuclear fusion, and then you see the products directly. Now, these are new atomic nuclei, and you have to recognize them from the ones that already existed. And radioactivity is an ideal tool for that, And I will talk about that. That's the bottom part where with gamma ray lines, you can basically see the radioactive decay of freshly produced nuclei. Conventionally, most of the database that chemical evolution is analyzing is the one that is marked in darker blue. That's stellar spectroscopy, where you look in stellar photospheres and the background light from the underlying star makes absorption lines from the material in the envelope. And those absorption lines, then they are giving us the abundances of all the different elements that we know of and have been shown in the previous graph. And these abundances, they are inherited from the formation of the star. So we always see in those stellar photospheres the gas as it was in its composition when that particular star has formed. Now there are other ways to measure. On the top you see meteorites. Meteorites have somehow ingested these newly produced nuclei and brought it into the solar system. So ingested as stardust that was formed probably near the source. And this stardust ended up in meteorites that are part of the solar system. So we have a sample from 4.5 billion years ago from material that was close to the solar vicinity. And then there are other observations of absorption and emission lines that help. Now, I'm talking about gamma rays. And so, so gamma ray lines come from radioactivities. And this is the table of lines that we can work with. You can say it's a short list only. It has less than a dozen of different radioisotopes. And they are sorted here by radioactive lifetime. So the most short-lived ones that would be interested in has a lifetime of on the order of 2 or 3 months. And that's the time it takes until one of those dense sites of nucleosynthesis is sufficiently diluted so that you can look inside and see the radioactivities. Because those nuclear fusion reactions, they happen in very dense environments. So even the gamma rays don't come out of the very short-lived ones. And then there are the longer-lived ones, nickel-56, you see. This is making all the iron that we have in supernovae. And then there's sodium-22, titanium-44. And the most long-lived ones, they have lifetimes on the order of millions of years. We can still see them with gamma-ray telescopes. And they are sufficiently abundant so that we can make measurements. And I will be talking about a few of those. Let me start with showing what Nikos mentioned earlier. On the top left, you see the pioneering detection of the aluminum-26 decay in our galaxy that was made or published in 1982 from the HEAO-2 satellite. And it was a germanium spectrometer. And since then, we have seen a rapid evolution of the field. On the right-hand side, you see for 2 of those isotopes, the number of papers over the years. And you see that the field started with predictions in the 1950s. Then after the measurements, there is a strong increase of the astrophysics work. And I think it's quite a lively field, even though it's a small field compared to other fields of astrophysics. Now, this satellite was a germanium spectrometer. It looked quite different than what you might know from general telescopes. And so let me take you to the principles of telescopes and to the instruments for a few minutes. Building a telescope in gamma rays is a bit more complicated than an optical telescope because you don't have reflecting surfaces, so there are no mirrors. And so what you have to do is you have to record the successive interaction of a gamma ray photon in a set of detectors. That's the only way how you can make a measurement. So the focusing or the imaging is actually done in analyzing all the detector events in your computer. So the telescope doesn't look like a telescope because it doesn't have any optics. The optics is done by analyzing the physics of the individual interactions. And we have, at the moment, we have 2 such instruments in space. You have to do that from space because the atmosphere is not transparent to those gamma rays. And the 2 instruments are the integral satellite that was launched 20 years ago and the New Star X-ray instrument that was launched in 2012. Now, these are all instruments that are already at their higher ages, and there are no future missions planned yet because this is a small field and it's quite expensive. But these are the instruments that we can work with at the moment. And you see in this set of pictures how such a telescope looks like when it works with the coded mask principle that we have in the spectrometer on integral. On the right-hand side in the middle, you see the camera. This is a set of germanium detectors, which basically has 19 pixels. So it's a pixel camera. And on the top, at about 1 meter and 70 centimeters above the camera, there is a coded mask that is shown on the top right. That's made of tungsten, and that basically casts a shadow onto this pixel camera, depending on where the source orientation is. On the left-hand side, you see schematics of that. And so basically, our measurement technique is to detect those shadowgrams from the sources in the sky. Now, this looks like ancient pinhole camera technology, and it actually is. And it would be easy if we had a sufficient number of photons to work with. But essentially, there are cosmic rays that hit the spacecraft, and those cosmic rays, they make all the spacecraft and the instrument material glow in MEV gamma rays. So we have a very high local background that's shown here. So this is an energy spectrum measured with the germanium detectors on integral, and it has is characteristic by about 400 instrumental lines. All those lines are instrumental. And the basis of analyzing such data is to understand this type of background. Here's a question. Mm-hmm. Fermi. Okay, the question was if Fermi doesn't have that problem. Now, the Fermi instrument works in a different way because it works at a higher energy. So it's working beyond the energy of this nuclear activation. As I said, nuclear binding energies are MeV. Now, when you work at GeV, that's a factor of 1,000 higher energy. And then you don't have this background from cosmic ray activation of the spacecraft. No, at TeV energy is even less. So you are far above the range of nuclear energies. While here with these telescopes, we are exactly in the range of nuclear energies. That's why we have this intense background. And so Fermi has, in that way, it has an easier task because this background doesn't exist, but Fermi also cannot address any nuclear physics. And so it's a different astrophysical goal. Now here, we have to deal with these nuclear lines. We have to understand them. And that is true for integral as shown here. And it can be done with good laboratory knowledge and good analysis. We have now basically 20 years of data to understand this instrumental background. And that actually works very nicely. And this is the example of the New Star X-ray telescope. You may think that in X-rays it's a little easier, but it's actually the same problem, that there is a large number of instrumental lines that have to be somehow addressed. Cosmic rays are not stable. The cosmic ray environment evolves. So this is a time scale of a few years, and it shows that the intensity of the cosmic ray irradiation of the spacecraft is actually changing with time with the solar modulation from solar activity that pushes the magnetic fields of the Earth in different regions. And so you have this variation. And that means that the spectral resolution of our germanium detectors also will be affected by cosmic ray irradiation. It will actually degrade, as you see from the rising slopes of all these curves. Now we have a trick with the spectrometer. Our colleagues in Toulouse have developed a technology of annealing so that every 6 months or so, we are heating the detectors to 100 degrees centigrade. Normally they are operated at 80 Kelvin at cryogenic temperatures. And with this heating, you cure the damages that are done by the cosmic rays. And you see that this works nicely. We have done that now almost 40 times, and the instrument still survives this thermal stress of heating and cooling. So this is quite impressive. And well, here is again the principle of measurement, and here is the equation that we have to solve when we want to analyze our data. So you have to take those measurements that are counts in your germanium detectors. You have to take those measurements as a function of the orientation of the satellite on the sky. Where does it point? So you have to understand your shadowgram. And this goes into this equation to explain the data measured per energy bin and per detector and per direction where you are pointing. So typically in this equation, you have to solve for the background. The background has to be modeled, as I said before, and it has some fitting parameters, and you have to solve for the intensity in the sky, which is the theta I parameter that is in front of the model of the sky. And this equation typically has something like a few million data bins, because you have to analyze many 100,000 spectra that are measured. But in the end, you get a spectrum shown on the bottom side that is the intensity as a function of energy to your model that describes the sky. And this sounds all very complicated, but it works. You can see here in the histogram that is in gray, the instrumental background in the vicinity of this aluminum 26 line. And on the bottom, on the right, with the red line, you see our deconvolved emission from the sky. And you see that the instrumental lines, that the two lines that are at 1765 and 1780 keV, those are perfectly suppressed. So the instrumental background doesn't shine through, but we can even distinguish a line that is underlying one of the other instrumental lines at 1.1809 energies. That's the green dotted line center. And you see that the line center from the sky is slightly off center from the instrumental line. So there's a very good discrimination possible. And so all these complicated instrument technology actually works. The same is true for New Star, where I showed you before the complex shape of the background. They have a different way of subtracting their background. They can do that. And on the bottom, you see that also there, the two decay lines from titanium decay are clearly shown here for the Cassiopeia A observations that I will discuss in a little bit. So this was enough about technology. Let's get back to astrophysics. So with this concept, I want to show you what we can learn about the solar system themselves. So I will start with supernovae. Let me start with type 1a explosions. Type 1a supernovae, they shine so bright because most of the new nucleosynthesis that is produced in this white dwarf deflagration turns out to be nickel 56, which is radioactive. And this is the decay scheme shown for nickel 56. On the left-hand side, you see the brightness curve in the optical, which rises with a maximum about 20 days after the explosion, and then it's falling off again. And this maximum comes from the envelope of the supernova absorbing the gamma ray emission from the nickel decay. And as the supernova explodes and dilutes, less and less of this radioactivity will be absorbed. And so the brightness fades away because the decay cannot make the envelope shine bright and being heated up by the gamma rays. So these observations of normal photons, they are indirect because it's the bolometer of the envelope of the supernova that shines. And you have to understand how the radiation transport works from the primary radioactive decay through the gamma rays and positrons and electrons into the thermal radiation that you see as optical. So it was always one of the goals to measure the gamma rays directly. And this was one of the goals that we had for all our instruments, but we had to wait until 2014 to have an opportunity of a supernova being close enough so that we could see the radiation coming from the characteristic gamma rays from the nickel to cobalt to iron decay. And this is a measurement that shows data points that were split in time. So the total signal is very significant from this decay. So we have seen the gamma rays, as I will show in the next slide, the spectrum. But here is the time evolution of the gamma rays rising with time as the radioactive decay determines. So the first 100 days or so, the envelope is not transparent to gamma rays because the optical photons have to be created somehow. So you have basically a complementing measurement of the optical in the gamma rays, because in the gamma rays you see the leaking out gamma rays, while in the optical you see the ones that are absorbed by the envelope and re-radiated. And so it's a very good diagnostics to have measurements like this. The precision is limited, but already with this you can say some of the models that have been advertised for the type 1a supernovae are less likely to agree with the run of these data points. Now we have a spectrometer, and so let me talk a little bit about a spectroscopy. On the top left, you see an overlay of two of the characteristic lines in broad energy bins, and you see that there is a very broad line that appears in the 1238 and 847 keV lines. It's broad because on the left-hand side of the top diagram, you see a narrow black line. That is the spectral resolution of our instrument. So you see that the lines are much broader than our spectral resolution. And so the top left is our discovery result. It's the spectrum where we reported we have seen the gamma rays from a type 1a supernova. And now on the right-hand side, you see how we in our group try to decompose that, making use of the high spectral resolution. So there are 4 different epochs. We start with the early part, 25 days after the supernova, and we end with 150 days. And these are spectra as a function of time in different energy binnings. We can go as high as we can on the left column using our energy resolution, or we can combine bins. And on the combined bins in the middle column, you see that there are these broad lines appearing, but there are some narrow spikes in addition to that. And so on the left-hand side, you see even more irregular. And so our claim from this is that it is not a smooth appearance of a Doppler broadened line, but there may be some 3-dimensionality in the explosion, so that you have some nickel clumps that appear closer to the photosphere early on and that have a different Doppler velocity than the others. And so this is an indication of the 3-dimensionality of the explosion appearing not as a homogeneously evolving sphere that gets transparent, but it may actually be a little bit more complicated. And that is supported also by other recent lessons on type 1a explosions. We have had an interesting additional discovery with this supernova. Namely, we saw the nickel lines from the earlier 8-day decay even very early after 20 days. And that would not be expected if a supernova evolves in transparency as according to the models, because after 20 days, it would be completely opaque and you would not be able to see any of the nickel that according to the models is produced at the very center of the supernova. Now, this was an interesting discovery that added, and so gamma rays have added some insights to type 1As. Now for core collapses, of course, our most prominent example is the supernova 87A. And you see on the top right how the light curve of a core collapse supernova also falls off in time, now re-radiating radioactivities of slightly different types, because you don't have only nickel-56, you also have other heavy elements that play a role. And at a later epoch, titanium-44 takes over, which has a decay time of order 100 years. It's 90 years. And so after a few years, the nickel-56 decay, basically nickel-56 has all decayed, and then others take over. And that fits the light curve quite nicely. And also here, it was very nice that NuSTAR could detect the titanium-44 decay gamma rays directly. Those are at low energies at only 68 and 78 keV. And so on the bottom left, you see the NuSTAR image of detecting this decay directly. a new star made an image, and this is probably a textbook example where you see also the three-dimensionality of a core collapse explosion, because the bluish areas, they denote the location of the titanium ejecta. And so you can see it's not a sphere that is expanding, it is individual clumps. And so in the Cas-A supernova, we have a direct witness of non-sphericity of core collapse explosions. Now these are the new star results. And so new star has very good measurements of even being able to look at the line positions. And there's some interesting kinematics that you can make, how the ejecta from the very inner part of the supernova actually get kicked out and explode. And that's an important lesson from titanium-44 decay that you cannot make otherwise. Now, titanium decay is shown on the top left here. It has 3 lines. 2 of them are accessible to new star. And there is a high energy line at 1.1 MeV that is only accessible to integral. And so for us, it was very interesting to be able to also detect this line. On the bottom right-hand side, you see our measurement for the high energy line that should match in brightness because it's coming from the same decay. It should basically have the same measurement. Now with this, you can make a Doppler velocity measurement because the Doppler effect scales with energy. So at the higher energy, you have a better constraint on the velocities. And I don't have time to go into details, but we have made the constraints for the low energy lines here and for the high energy lines here. And you see from the green marked laboratory energies that in both cases, we see from Doppler velocities that there is a global redshift. So the bulk of the ejecta of this Cas-A supernova are actually moving away from us. They are expanding towards the backside of the remnant. This is interesting lessons for core collapse physics. There's another interesting lesson from the total abundance. This is a graph that I think Nikos once invented. It shows the titanium abundance and the nickel abundance as they relate for different objects. And you see some data points on the top that show supernova 87A and show the Cas-A remnant. And those measurements, they populate an area that is not really compatible with the black dots that are the different models of stellar evolution and supernova explosions as you would have them from theory. And so only when non-sphericity is incorporated in the core collapse model, as shown in these red stars, then you get close to the domain of data points measured from the 2 core collapse explosions that we have good measurements on both those radioisotopes. So that's an interesting additional diagnostic based on different messengers, including the solar abundance, that is the dotted line, that's shown in purple here. And so this is the way we learn about supernovae. Now, in the last part of my talk, I would like to talk a little bit about how we can trace the flows of cosmic matter. You see in this cycle diagram on the top left that you have to return material from explosions into newly forming stars. Now, explosions, they create matter at temperatures of, say, at least millions of degrees. So it's hot plasma, it's fully ionized plasma, and that, of course, doesn't form stars. So you have to find a way to lose the energy through some cooling mechanisms and transport this hot stuff into the star-forming gas in the cold part of galactic gas in giant molecular clouds. And it's, of course, interesting to look how that happens, because you cannot take for granted that all of the gas in a galaxy is homogeneously mixed. And whenever a supernova explodes, you are going to see that in the next generation of forming stars. It's not as easy as that. And so here come into play the more long-lived radioisotopes that we have. And this is the image and spectrum of the aluminum-26 decay. The image was obtained with the Compton Observatory, as is shown on the bottom left. And that is a result from the 90s of the last century, this image shows how the galaxy looks like in radioactive decay from 1 million years lifetime. So with this image, you see directly that currently in the current galaxy in the last 1 million years, there has been star formation, nucleosynthesis ejection from star formation. You see the radioisotopes radiating, so there must be some ejection in the last 1 million years. So currently, the galaxy is active as a nucleosynthesis source. And the image shows some interesting granularity, I would say. So it's not as smooth as you know it, for example, from infrared stars. It's not as smooth as you would expect from very numerous sources like nova explosions, which explode at a rate of 30 per year or so. It is reflecting some irregularity that matches more closely what you expect from groups of massive stars, or from massive stars in general, because massive stars are short-lived. And so you're going to see a picture that is not a steady state picture, but rather a current picture of stellar activity in our galaxy. This is why at the time Nikos and myself made that statement in one of the papers. We believe from this image you learn that this is massive stars and their supernovae that you are seeing there. Now, an interesting measurement of velocities could be made again with the high resolution spectrometer, which shows on the right-hand side a series of aluminum line measurements now pointed in different directions in our galaxy. On the left-hand side, you see the top view of the galaxy, and you see that when you look in the part of the galaxy where the galactic motion is actually receding, then you're expecting a redshift, while in the other part of the galaxy, you're expecting a blue shift, and that is actually what is reflected in this Doppler effect of lines. So it's a large-scale galactic rotation that we see here, because we didn't discover it, but we were surprised to see it with that clear signal. You will see the surprise when I show you this overlay here. The blue data points that are shown here, they are our measurements of velocities as a function of galactic longitude. And the surprise was because these velocities are much larger than what you would expect from what we knew about galactic rotation beforehand. So the colored part here shows what you know from carbon monoxide, from CO measurements. This is cold gas, and we know galactic rotation from very precise catalogs of molecular clouds, and they don't reproduce what we see in the radioisotopes. So something new is to be learned here. And of course, our first thoughts were maybe we had a systematic problem in our data analysis, but later we came to this solution here. Let me take you through the sketch on the top right. On the top right, you see an illustration of yellow stars that would be formed, as Nikos said before, in the spiral arms of a galaxy. That's typically where most of the star formation happens, because the giant molecular clouds are compressed by the spiral arm potential. And so that leads to star formation and newly forming stars, including massive stars. Now, as these stars evolve, they will not stay at the same location in the galactic potential. They will carry their momentum further. And as it happens in our galaxy, galactic rotation is such that in the timescale of a few million years, the massive stars occurring in groups, they would be located at the leading edge of the spiral arm potential after typically 5 million years. That is an offset. And this offset has an implication because as these stars going in their wind phases and in their explosions later, they will blow cavities around them. The typical H2 regions will be blown, and they will be blown in a region that basically sits on a slope of the gravitational potential, because we are not sitting in the center of the spiral arm. And so there is a tendency for these wind cavities to be asymmetric, having a forward extension that is a little further than the backward extension towards the higher potential of the spiral arms. And it's this asymmetry that made us explain the measurements that we see, because this asymmetry means that the ejecta from supernovae in those cavities, they have a longer time to propagate in the forward direction of galactic rotation before they will be decelerated by denser material. So they are expanding in a cavity at the velocity of their ejection of, say, a few hundred to 1,000 kilometers per second, and they expand for a longer time in the forward direction than in the backward direction of galactic rotation. And that leads to an excess velocity component of about 200 kilometers per second. Now, this is radioactively decaying material, and this is why you, of course, get an exposure effect that looks at the first part of the trajectory of this material, because in the late part, it will be decayed and it will not shine in gamma rays anymore. And that gives this effect. So with this explanation, we can say that we have detected the effect of superbubbles being the typical environments of nucleosynthesis sources. And these superbubbles, they are between the spiral arms, as shown in the left-hand side in an illustration, and they probably also lead to blowout into the galactic halo. Now, of course, with our Doppler velocity measurements, we are looking in the plane of the galaxy, so we don't see the halo component because it's perpendicular to the line of observation, so you don't get any Doppler effect. But it's interesting with this measurement to have some evidence of the superbubbles being so important. And on the bottom left, you see one of the inhomogeneous chemical evolution models from a galaxy simulation where radioactivities were incorporated, and that surprisingly also reproduced the run of our data points. So there's some interesting things to be learned about how the interstellar medium actually is shaped by such feedback of stars. There are some simulations, like from the Krumholz group in Australia, that made simulations for radioactivities in aluminum and in iron-60. And you see here that the galaxy is visible, but you also see these characteristic blowouts into the halo that shows in simulations. And that's the most spectacular effect that is seen in such simulations, because the simulations have to make some assumptions about a normal galaxy, about where the spiral arm potential is. And the inner galaxy, for example, is completely excluded in those simulations because it would be too complex. But still, you see the essentials of superbubbles acting. Now, comparing such a simulation with our observations is a little difficult because of the assumptions that the simulations make and because of the local bias that we would have in our observations from local material. And we have made some analysis of how to compare such data, but let me skip that in the interest of time. And let me rather come to a second radioactivity that I want to address briefly, and that is iron-60. So what you see here is a Kippenhahn diagram of stellar evolution. This is a massive star as it evolves from the left-hand side of its formation to the right-hand side of its supernova explosion. And this is a log scale. The log scale of stellar evolution emphasizes the complex late parts of stellar evolution where all the different nuclear burnings happen for heavier isotopes. So in the beginning, there's the main sequence phase where the bluish part shows the core of the material burning in hydrogen. And then there's the hydrogen shell burning going on till later times. And the same happens for helium core burning with helium shell burning. Here are all these complex burnings of the later phases. And the arrows, they show you that aluminum-26 is produced in hydrogen burning in the main sequence phase and also in the explosion and in one of the late burning phases. Iron-60 is produced only in helium and carbon shell burning. And you see from the evolution that you normally don't get all of these materials out, because getting something in the wind, you need to mix it into the wind from the core. And that's a long way from the core to the envelope. And so some of the aluminum-26 can be mixed into the Wolf-Rayet wind, while all the other material from nucleosynthesis only comes out as the star explodes. Making a measurement of the ratio of aluminum-26 to iron-60, you actually get some information on this picture here. Is this picture correct? Does it show the right mixing and evolution of a star, or is it not? And so we made measurements for both these radioisotopes. On the left-hand side, you see an energy spectrum now binned in a way to just emphasize the radioisotopes. So the line here is the aluminum line, and these are two lines that come from iron-60 decay on the lower side. So with the integral spectrometer, we can make a measurement of the ratio. We can constrain this ratio as shown on the right-hand side. And this looks a little bit more complicated because you have to make some assumptions about the spatial distribution when you make such a ratio measurement. And that introduces some uncertainty in the result. But in general, this is a zoom picture showing a region around 20% or so of being the brightness of iron-60 compared to aluminum. And we can say this ratio with all the systematics included is smaller than about 40%. So we have an upper limit on this, and that already will tell us a lot about this massive star model. Now, let me come back in the end now to superbubbles again. Superbubbles, I showed you, are important agents. And here is a sketch of the example, the example of a very nearby superbubble where we know a lot more about than all the superbubbles in the distant part of our galaxy. This is the Orion region with the Eridanus cavity. And you see in black the Orion molecular clouds. You see also that here is a group of massive stars. This is the Orion OB1 association with its subgroups. This is on the near side of this molecular cloud. And you also see here illustrated a cavity. This cavity is nicely delineated in measurements of atomic hydrogen. So we know the geometry of this superbubble from several different astronomies quite well. And we can study it. We can look at how we can now get a coherent picture. On the bottom right-hand side, you see that we have measured aluminum-26 from this superbubble as well. We have isolated the signal, and we are trying to refine that measurement to make a velocity measurement only for this one group. Because what you would expect is that the aluminum would be expanding into this cavity, and this cavity is oriented from the molecular clouds towards us as an observer. So one would expect a blue shift of the radioisotopes as they expand into this cavity, and that's the target of our measurement. We have indications of a blue shift already, but this is not yet significant, and it takes many years of observing to get a signal that is significant enough so that you can make a better measurement. But we are working on that. Now, we have also made simulations of such a superbubble as it happens around a group of stars, and you see this simulation animation running here. So when massive stars occur as a group, then their cavities will quickly overlap, and then the dynamics and the expansion of a cavity will be very different than from a single supernova explosion that has to be worked into such a study as well. This is not the only superbubble that we have nearby. Here is an illustration of the solar vicinity and the SCO-SEN association. That's an association that is even closer than the Orion region, but it's also a little bit more confusing because it's so close that the objects, they cover a large portion of the sky. And so it's difficult to make precise observations for all the stars and for the gas. But we have combined the aluminum observation with optical observations, with X-rays, and with hydrogen observations to try and understand this. And from this, we developed a picture that there is a successive star formation happening, reflecting the superbubble activity and how the superbubble wall collides with nearby molecular clouds. And this is another confirmation of this superbubble scenario around massive star groups. And I think this is now taken up also by other groups. You see here simulations of superbubble size distribution. And this shows that typical cavities, on the left-hand side, you see a graph. When they are young, they are expanding. This is the rising part of the smaller bubbles. And when they get bigger, then they nicely make a power law that extends to up to kiloparsecs. So superbubbles with sizes of a few hundred parsecs to kiloparsecs are important agents in how to bring back material. We have, in our group, tried to incorporate all this knowledge into a bottom-up model of how the aluminum-26 sky would look like. And so on the bottom left, you see the nucleosynthesis output of a stellar group in terms of aluminum-26 with different lines showing different models of nucleosynthesis. And we have used this knowledge of what a massive star group does in terms of theory, and we build it into a population synthesis model, modeling individual groups of massive stars in our galaxy. We have combined this with a catalog of massive star groups as we know it from the solar neighborhood out to a few kiloparsecs. And for the more distant galaxy, we have done a Monte Carlo. So this is a bottom-up model of using the knowledge of the solar vicinity, using the knowledge of theory, and build it into a model that in the end gets us a simulation or a bottom-up model of what the aluminum sky should look like. We can do a lot of diagnostics of such population synthesis, like comparing different models of explodability of stars. This is the top diagram, or of additional yields for binary systems, which is the bottom diagram. And I don't have time to discuss all the details. I just want to show you the end result. This is the bottom-up model of our galaxy of the aluminum sky with the known nearby groups on the bottom right-hand side. So these are the stars that are as close as Scorpius Centaurus or Orion. So all the nearby ones that we know exactly are the bottom right ones. And the total sky is shown on the upper part. And when we compare that with our image, then we would say there are some similarities that are encouraging, but what we found is that the all-sky brightness that we measure in the aluminum line is just much higher than the predictions show. And you see that on the bottom right diagrams. When you play with the star formation activity, then you have to crank up star formation to up to 8 solar masses per year in order to get the total flux that we see. So there is some deficiency in the case of aluminum. In the case of iron 60, we get basically the brightness from this bottom-up model that we actually measure. So there we seem to be okay, but with aluminum, something is wrong. So this is also adding a constraint on this ratio, but it could also be a local effect of our particular situation. And we have done some game with that is shown on the bottom left graph. I'm almost done, yes. On the bottom left graph, this shows that when we take our bottom-up model and we basically rotate it around us as an observer, then we see an effect at one particular orientation where one of those nearby cavities actually gets all around us and adds a significant flux because we are all of a sudden inside such a cavity. And that brings us into agreement with the measurement. So it could be a local effect like the local bubble that is shown here. In a recent paper from Zucker et al., you see how the local bubble is understood. This is a cavity that the solar system is embedded in, and it has a size of typically 200 parsecs. And maybe that is the part that is distorting us. And this is interesting because it relates our work to another work That is the detection of iron-60 in the current Earth crust, in the ocean crust. Ocean crusts are shown on the bottom left. And in such an ocean crust, there have been measurements of currently live radioisotopes. This is iron-60 with a decay time of about 4 million years. And it has been detected. So it was recently deposited onto the Earth, onto the solar system. And that's a very nice set of measurements that shows that when you do some backtracing in time, that there has been some intensity changes, like a maximum about 3 million years ago, and maybe a second maximum 8 million years ago. So maybe the wall of the local bubble has actually swept over the solar system at those two occasions, or maybe there were some nearby explosions that are reflected in these deposits. And so with this, I would like to end. I had a small part on positrons that I will skip now in the interest of time. And I just want to show you my summary. And I hope I showed you that with those gamma ray observations, we actually make complementing information. We are collecting this about how supernovae explode and how material flows back from new nucleosynthesis sources into the cycle of matter. And with this, let me thank you for your attention, and I invite questions now.
So thank you, Roland, for this. Thank you very much for this panoramic view of astrophysics with radioactivities. Now, are there any questions from the audience? Yes, please. You have okay.
Hello. Okay. Yeah. Thank you very much for the talk. I really enjoyed it. So I just had a question about the velocity curves. How you were saying there was a difference between the aluminum measured and then the ones for the molecular clouds. Mm-hmm. And so if they're to be explained by these superbubbles, is it possible to apply a correction factor or removing the superbubble contribution of the velocity? And could you make the molecular cloud velocity align with the aluminum velocity again? Has that been attempted yet?
There is a fundamental difference of what you are measuring. We are measuring a decaying isotope. And so we are actually averaging over typically 1 million years of the velocity behavior. And of course, you could look for the late part, if you like, but you would that would be the material that already basically reached the cavity walls. And that's the lowest velocity that you would expect. And this velocity should match the CO velocity. But we cannot spatially resolve that. So our resolution in gamma rays is typically 3 degrees, and that's insufficient for resolving spatially. And so we cannot make that. We basically get the cumulative averaged velocity from a region like a few degrees across, and that always will be a large part of the superbubble. So what you ask, we cannot do.
All right, thank you very much.
Mm-hmm.
For neutron star merger 170817, strengths, I know that only one line was observed, which was a strontium line. I don't know how you look to see with your knowledge of the explosion and so on and so forth, what we can really learn about this type of explosions and the mergers.
It's a very good question. Actually, you say that the strontium line was observed. It depends how you look at it, because these lines are velocity broadened, and there's an indication of an absorption feature that could be in the region where you might expect a strontium line. I don't think it's a clear measurement. It's an indication of heavy elements playing a role, which is reflecting also the infrared energies of the radiation that came off of this kilonova. Now, of course, that was an atomic line, so it's an absorption line, and you don't know if that strontium has been freshly created or it was in the envelope of the neutron stars anyway. So we have to learn a lot about those neutron star mergers, and of course, observations of radioisotopes would be a clearer signal of freshly produced material. There are a few radioisotopes that I listed also in my table, but this kilonova was at a distance of 40 megaparsecs, which was already quite close. And for our gamma ray instrument, you would have to move it at about between 3 and 5 megaparsecs to be able to see those radioisotope lines. So this is just too distant for gamma ray telescopes at the present time and even for the future. We can build gamma ray telescopes now with current technology that are maybe a factor of 100 more sensitive, but even that would be insufficient. And so for neutron star mergers, I think there is almost no hope that you can learn a lot. Even in the optical, this was a great opportunity because it was so close. And the typical distance to neutron star mergers is anyway much larger. So I think, unfortunately, the gamma rays would be a clearer signal. If it happens in a nearby galaxy, then we would have a good lesson. But I think neutron star mergers will stay with us as enigmatic objects for a long time.
A technical question, if I have time. Why don't you, for the detectors, why don't you use, for instance, the type of detectors which are used in particle physics? For instance, multi-wire chambers, or colorimeters, because they are, when this is not possible if, for instance, for X-ray, but for gamma ray in MEV range, it's possible to use especially multi-wire chambers or especially colorimeters. I don't know if is there any technical reason why it's not used in astronomical
We actually do have a colorimeter. We have these detectors and they record the energy of the gamma ray photon. So that's a colorimeter. We measure the total energy.
Okay.
But you need a second piece. You need directional information. And how do you get directional information from a colorimeter? You don't. So in the case of Fermi, what you have, in the case of Fermi, you have a bifurcation of the two leptons that are created by pair creation. And that's the trick for GeV radiation to get imaging information. Now, the pair creation only works at energies which has a threshold of 1 MeV. So at 10 MeV-ish or so, you could start to use that technology. Below, you depend on other interactions that photons have with matter. And the most prominent one is the Compton scattering. And the Compton telescope is actually using this scattering as imaging information. And that's the most promising way of building future instruments. Yeah, I said it's a dream because we have the technology, but now we need community support. And you saw that James Webb was just starting to operate, and you saw the cost of James Webb. Now, do you think that you can get this kind of money for a Compton telescope that measures?
Very difficult.
Yeah, so it's not so easy.
Okay, so is there any other question from the Zoom? No?
Sorry? There is some chat, but
discussion.
I think it's mostly about the quality of the audio.
Oh, yeah. No?
Okay.
Okay. So thank you very much again. I have a last question. So what's your feeling now about the field? after all you presented there, you say it's a dream, 2040, but while waiting for that dream?
Well, I'm actually an optimist. I think that this is why I emphasize this superbubble discussion, because it's coming also from the infrared community and from the star formation and molecular cloud lifetime community. There's a recognition that you have to learn more detail about stellar feedback and how it happens. And stellar feedback is reflected only indirectly in, for example, dust temperatures or things like this. It's reflected much more directly in the radioisotopes. And so this is one direction where I think we will get support from the broader community. And there is a lot of studies about the early solar system. We don't understand how the sun was formed, and also there radioisotopes play a role. So I think there are several areas where radioisotopes are an important diagnostics. Cosmic rays is maybe another one. And I think that it will take some time until the community at large recognizes the usefulness of this astronomical window of nuclear radiation. We have so many astronomical windows. We have just opened the gravitational waves, but in the nuclear radiation, we basically allow a gap of astronomy. And I think that recognition will hopefully spread. And that's why I'm optimistic. Maybe I may not experience it in my lifetime because I'm already now at retirement age, but
yeah, what I hoped is that you would say that, and I was expecting you to make that statement. I think this is the message, in fact.
Yeah, I think it needs a community, it needs a study, it needs a recognition of multi-messenger astrophysics and how to combine these things.
Okay, thank you very much for the presentation and for everything. Okay, thank you.
Thank you.